Hello again. In the last lecture we talked about key exchange and what the problem was and how you might solve the key exchange problem if you have a public key infrastructure in place. But suppose that you don't. Well, this was one of the first problems that was addressed by a cryptographic protocol. And a solution was invented in 1976 by Diffie-Hellman, and it's called the Diffie-Hellman Key Exchange protocol. Okay. So notice that this was prior to the invention of public key encryption, so they didn't have the option of using public key stuff to accomplish this. So what's the point? You have two parties that want to communicate with one another. There's no public or private keys anywhere in sight, and so you want them to be able to agree upon a key that they can use for symmetric encryption. The problem is that somebody may be overhearing their conversation, and so you want them to come to an agreement on a shared datum, but you don't want anybody who's overhearing their messages to be able to figure out what that datum is. That's the problem. Okay, so they came up with a really clever algorithm for doing this. So suppose we have Alice and Bob, A and B here, and they're trying to agree on a value that the eavesdropper, Eve over here, can't get. Okay, so what they do is they agree on a prime number P and a base G, and they can publish these and disseminate them, send them back and forth. And then Alice and Bob both choose a secret number which they don't disclose. So A is known only to Alice and B is known only to Bob. And then Bob raises G to the bth power, which is his secret number, mod P, sends that value to Alice, and then Alice does the symmetric thing. So they both have the other's computation. And then by the combination of those two computations, they can come to an agreed upon value. And this is true because of the way that modular exponentiation works. So let's see an example here. Alice and Bob agree that P is going to be 23 and G is going to be 5. And by the way, these numbers are hopelessly small to make this secure, but they illustrate what we're doing. Alice chooses a particular number, say 6, and Bob chooses a number 15. So Alice sends to Bob G, which is 5 raised to 6 mod 23, which is 8. And Bob sends to Alice 5, which is the base, to his number 15 mod 23, which is 19. Okay, so now they each have each other's computation. And then Alice computes 19, which was Bob's number, to 6, which is her secret number. And Bob computes 8 to 15, which was his secret number, and they both came up with the same answer. Now, the answer they got was 2, which would clearly be too small, but the problem here is that an attacker, even hearing all these messages go back and forth, couldn't figure out the value 2. So how secure is this? Well, suppose P, which was the prime modulus, is around 300 digits, excuse me, and A and B are each around 100 digits. Well, then discovering the secret value that they compute would require longer than the lifetime of the universe by the best known algorithm that we currently have. This is called the discrete logarithm problem. Okay, so what's the problem that we're trying to solve? How can two parties agree on a secret value by the exchange of messages, even when the eavesdropper may be able to hear all of their messages? Well, the Diffie-Hellman algorithm, which we described in this lecture, accomplishes this, and actually it's still very widely used, even though public key infrastructure is broadly available. And if you have sufficiently large inputs, Diffie-Hellman is a very secure algorithm. Thanks.